Good day friends, welcome to my YouTube channel. Today our topic is the application of Coriolis force and the centrifugal force, right, that we have studied in our previous lecture. So let's have a quick repo. Let's revise it, that what we have studied in Coriolis force. So as we have discussed that Coriolis force is basically a pseudo force which is acted and which can be observed by an observer who is on the rotating frame, right? And the direction of this force is perpendicular to the axis of rotation, right? And where can we see the Coriolis force? Now let's consider the frame of reference of Earth. Now, as we all know that Earth spins on its axis of rotation, right? Now, due to this spinning, what happens? The air which is flowing from the equator to the poles, they get deflected, right? Like this. Now, look at here, as it is clear from the diagram, right? That the air which is flowing from the equator to the north pole, either north pole or south pole. So what happens? Because of this Coriolis force, it gets deflected, slightly deflected, right? As you can see in the diagram, it gets slightly deflected. Here comes the role of Coriolis force, and this is known as Coriolis effect. Correct? I hope the point must have been clear. Now let's take a numerical problem in which there is a disc, a uniform solid disc, right, which is rotating around the axis of rotation. Look at here. This is a disc, uniform circular disc, which is rotating around this axis of rotation, and the angular velocity of this particular disc is omega. The radius of the disc is capital R, right? And the question is, there is a smooth disc, uniform disc of radius capital R. A small ball of mass m is kept in a groove made along any radius, right? So this is a groove, and there is a small ball of mass small m is kept inside this groove. So what will happen? You can imagine the situation when the disc starts rotating. So what will happen? There is a tendency of this ball to move along the groove and to come to the circumference, right? Now let's understand it once again. If initially the ball is kept at a distance small r from the origin, now this is the origin, this point is our origin. What do we have to calculate is basically find out the velocity of the ball when it reaches to the circumference. Means we need to find out the velocity of this particular ball when it reaches to the circumference, right? Now this particular problem can be solved by considering a variable position, right? Means this particular ball is moving right from this particular point to this particular point due to the spinning of this disc, right? This disc is spinning like this. So definitely the tendency of this ball will be towards this circumference, towards this particular point. So from O to X, this small ball will start moving, right? So the position of this particular ball keeps on changing every time, right? Now let's consider and take the frame of reference of this rotating uniform disc, right? So now first of all, let's analyze that how many forces are acting on this particular small ball when it starts moving. So first of all, its weight will be there, right? The weight of the ball must be there. Then the reaction force of the disc, correct, which is perpendicular from the surface, like this, means weight mg. This is your weight mg downward. Then the reaction force of the surface of this disc, right? Then the reaction of the side walls, right? Side walls means if groove is there and let's suppose the ball is inside and it's moving, so what will happen? There will be a reaction force of this side walls, right? Which will be parallel towards z axis. Yes or no? Now this reaction of this surface, which is perpendicular from the surface of this uniform disc, its direction will be parallel to y-axis, but the reaction of the side walls will be parallel towards z-axis. This point is clear? Now, apart from this, there is another force that is known as centrifugal force, right? Due to this centrifugal force, which is directed towards this particular point, towards the circumference of this particular uniform disc, correct? Because we all know that the direction of centripetal force is towards the center, but the direction of centrifugal force is opposite to the center of rotating frame, correct? So the centrifugal force, that will be mx omega square. Now let's consider that for a particular instant or for a particular time, the distance or the position of the ball from the origin is x. Now x is a variable, correct? So the centrifugal force acting on this particular ball will be mx omega square, right? And its direction will be towards ox, correct? The next force which is acting on this particular ball is the Coriolis force. What is that? Is Coriolis force, and its direction must be perpendicular to the axis of rotation, right? So this is the axis of rotation, and the Coriolis force will be perpendicular to this axis of rotation, right? And it will be towards z direction. Of course, this one is clear. So it will be perpendicular to both, towards to the x-axis as well as the z-axis, correct? Now let the initial position of the ball is x from the origin, that we have already discussed. Now let's take a particular instant that it is x distance apart from the origin, correct? This particular ball is x distance apart from the origin, correct? So the net force acting on this particular ball will be these many forces, but as we have to discuss about the movement of this particular ball, because this is the ball can move only in x direction as shown in the diagram. Look at here, this ball is free to rotate, to move only in ox direction, correct? So on this along this direction, let's suppose the net force is F, which is equal to mass into acceleration, and the differential form of acceleration is rate of change of velocity per unit time. What is that? It is F is equal to ma, which is equal to m times dv over dt. This must be equal to the centrifugal force mx omega square, right? Now what will be the next step? It will be like this, m times